Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing about power transistors and especially BJT. So in this lecture, we will be seeing power transistors, and these are further classified into BJT, IGBT and MOSFET. And for now, in this lecture, we'll be discussing about BJT and in detail what is the symbol of BJT, structure, input as well as output characteristics of BJT. And firstly, BJT, as I already told you, power transistors are further classified into BJT, MOSFET and IGBT, where BJT stands for bipolar junction transistor. MOSFET, it is metal oxide semiconductor field effect transistor. And then we have IGBT as insulated gate bipolar transistor. And then power transistors. So I have already discussed in my early lectures, like diodes are nothing but uncontrolled devices. We don't have any control over the diode, and it is simply an on switch and off switch, where we cannot control the output voltage which is actually fed to load. And then we have seen SES, which are nothing but semi-controlled switches. Only turn on time has control, whereas turn off has no control. And then we have seen about transistors as well. Transistors, these are nothing but fully controlled devices. Why am I calling it as fully controlled device? That is, turn on time as well as turn off time of the transistor can be controlled using a base drive. That is, as long as the base drive is provided, in that case, transistor will remain in the on condition. The moment when we withdraw the base drive, the transistor will come into the off state. So that is the reason power transistors are nothing but fully controlled devices. And here, if you see, switching speed of the transistors are higher when compared to that of the normal thyristors. These are much speeder when compared to that of the normal thyristors. And transistors are now available with high voltage and current ratings. But when we compare to that of the thyristors, the voltage as well as current ratings of these particular transistors are less when compared to that of thyristors. So that is the only reason transistors can be used in low and medium power applications. Now, let us see in detail about the BJT. BJT, these are nothing but current control devices, and it has got large current handling and power handling capability when compared to that of normal BJT. I have already explained in my early lectures, normal BJT are operated for very less ratings. Whereas these power BJTs has larger cross-section area, and these will be handling the higher power ratings. So that is the reason the cross-sectional area of these power BJTs will be more when compared to that of normal BJTs. And it has got a vertically oriented structure which has higher power handling capability. And for now, let us see the symbol of the BJT. And if you consider the symbol of the BJT, here we have, we have two types, that is PNP transistor as well as NPN transistor. And here, if you see, always arrow indicates the current direction, and here always it is given for the emitter itself. And if at all, if the current direction is showing inwards, in that case we call it as PNP transistor. And if at all, if this particular arrow direction, if it is showing outwards, in that case we call it as NPN transistor. So that is the basic difference between PNP transistor and NPN transistor. And here transistor, bipolar junction transistor, has got three terminals, namely emitter, base and collector. But here NPN transistors are more preferred when compared to that of the PNP transistor? It is because it is easy to manufacture, and at the same time it is cheaper when compared to that of PNP transistors. So that is the only reason why we widely make use of NPN transistors. And then we have, see, this is a normal BJT which will be used for handling low power applications, whereas here we have power BJT. And if you see the normal BJT, it is a 3-layered device, and it has got 2 junctions, and it is a 3-terminal device, namely emitter, collector and base. And if you consider the power BJT, it is a 4-layered device. And it has got 3 terminals, base, emitter and collector. And if you see the bottommost layer, it is N+ layer, and it is the doping level of this particular N+ layer is about 10 to the power of 19 per centimeter cube. And thickness of this particular N+ region is about 250 micrometer. And if you consider N- region, and it is lightly doped, and the value of the doping level of this particular N- region is 10 to the power of 14 centimeter cube. And the thickness of this particular layer is about 50 to 200 micrometer, and this is termed as collector drift region. And this collector drift region determines the breakdown voltage of the device, and this is very important. And if you see, this is the additional layer when compared to that of normal BJT. In normal BJT, we only have NPN layer, whereas power BJT, we have N+, N is common, and here P is common, and here N is common, and in addition we are connecting an extra layer, that is N- layer, which we call it as drift layer, which determines the breakdown voltage of the device. This is an additional layer which is being added, and here if you see this plus, this represents the heavily doped, and if it is minus, in that case it indicates lightly doped. And if you see there is no plus or minus found, in that case it is moderately doped. So here base layer, it is moderately doped, and here N+ layer, that is emitter as well as collector region, is heavily doped. So here if you see P layer, doping level of this particular P layer, it is given as 10 to the power of 16 per centimeter cube, and whose thickness is given by 5 to 20 micrometer. This is the base thickness. And then we have emitter, which is N+ layer. The doping level of this particular N+ layer is high, and it is 10 to the power of 19 per centimeter cube, and whose thickness is given by 10 micrometer. So this is all the structure of the power BJT, and here this power BJT has negative temperature coefficient. It has got negative temperature coefficient. And talking about the voltage and current ratings of this particular BJT, it is given as 1200 volts. It will be operating at 1200 volts, up to 1200 volts, and current with the current rating of 800 amperes. And it has got secondary breakdown, and it has got high switching speeds and low conduction losses. This is the advantage, that is, it has got high switching speeds as well as low conduction losses. And then, as I already told you, this is a current control device, and the power handling capabilities of power BJT will be about kilohertz, which is very high when compared to that of normal BJTs. And here the term bipolar, the BJT is abbreviated as bipolar junction transistor. The term bipolar means the current conduction is due to both holes as well as electrons. So that is the reason it is named as bipolar. And as I told you, this is a 4-layer, 3-terminal, 2-junction. It can be a PNP or NPN. And here NPN is widely used out of it is because it is easy to manufacture and at the same time it is cheaper to buy. And then let us see the input as well as output characteristics of BJT. And here if you see the input characteristics, that is IB, base current, input current, base current, IB versus input voltage, that is VBE. If you consider, see here, this is how the BJT looks like. And here we are considering the NPN transistor. This is the emitter terminal and this is the base terminal and this is the collector terminal. So here what always emitter is made as common. This is the common emitter configuration where this is the most popularly used configuration. So here what we are doing is, this is the input current IB versus input voltage VBE. Input voltage VBE. So input characteristics is the graph IB versus VBE, and maintaining output voltage, that is VCE, is maintained constant. VCE is maintained constant. Say we are setting the voltage of VCE at particular voltage, say 5 volts, and now this output voltage is maintained constant, and we start increasing the input voltage in steps such that at some voltage this particular depletion layer breaks and it starts conducting current, and IB is increasing, and that is how, see, if you see the characteristics of this particular input characteristics will be similar to that of the diode curve. And here later I'll start increasing the VCE to, say for example, let us increase it to 10 volts and now maintain it constant at this particular 10 volts, and let us start increasing the input voltage in steps such that at some point this particular depletion layer breaks and it starts conducting a current. And if you see here, VCE2 is greater when compared to that of VCE1. So these are the input characteristics. Talking about the output characteristics, here output current is IC. So output current IC versus output voltage VCE. Output voltage VCE. So this is nothing but output characteristics graph where maintaining input current constant. That is how we obtain the output characteristics, maintaining input current constant. That is IB is nothing but your input current where IB is kept constant. So initially what we'll do is we will set IB is equal to 0. We will set IB is equal to 0. When base current is 0, in that case it will be operating at cutoff region. It will be operating in the cutoff region. Since IB is equal to 0, in that case there is no output current and only certain amount of leakage current will be flowing through the device in this particular cutoff region, and the range of this particular leakage current will be in microamperes, which is very less. And basically the transistor BJT will be operating as an off switch in this particular cutoff region. It will be operating as an off switch. Okay, what is the condition? How we can achieve this particular cutoff region? That is, we have a condition which is to be satisfied. That is, during cutoff region, emitter to base as well as collector to base region need to be operated in the reverse biased mode, such that we can achieve this cutoff region where IB is equal to 0. In that case, output current is also 0 and it will be operated in this particular cutoff region where it acts as an off switch. BJT acts as an off switch. And then we have other modes as well. Let us see each in detail. See, this is the cutoff region where the base current is equal to 0 and collector current will be equal to that of the leakage current ICE0. This leakage current is basically due to the minority charge carriers. And the region below this IB is equal to 0 is nothing but cutoff region, and BJT offers large resistance to the flow of current. So hence in this mode, transistor, it will be operating as an open circuit, or we can also call it as off switch. So that is all about the cutoff region. And then we have active region. Okay, how to achieve this active region? Firstly, active region whenever emitter to base and collector to base region. If you make emitter to base region into the forward bias mode and collector to base region into the reverse bias mode, in that case, we can achieve this active region. And here in active region, what happens? Initially, the current will be increasing slowly and later it will become constant. By going on increasing the base current, we can increase the collector current and it will be increasing and later it will be becoming constant. So here if you see, IB5 is greater when compared to that of IB4. IB4 will be greater when compared to that of IB3 and so on till IB1. So as we go on increasing the base current, IC will be increasing in this process and this region we call it as active region. So in this active region, basically the transistor will be operated in this particular amplification mode. Amplification mode where in power electronics, when we are concerned with the power electronics, we don't have that amplification applications. We don't use amplification applications much in power electronics, whereas we are much concerned with cutoff region as well as the saturation region, where saturation region transistor will be operated as an on switch and cutoff region the transistor will be operated as an off switch. So that is the reason we are more concerned with the saturation region as well as cutoff region, whereas we are not much bothered about this particular active region where the transistor will be operated as an amplifier. So here in this particular active region, transistor usually used as amplification mode. And then we have this quasi-saturation region. What is this quasi-saturation region? How it is actually achieved? When the emitter to base as well as collector to base region both are made forward biased, in that case we can achieve this particular quasi-saturation mode. So here in this particular quasi-saturation mode, this lies in between hard saturation as well as active region. Hard saturation as well as active region, quasi-saturation mode can be achieved. And if you see, if we increase the current beyond as that of IB5, in that case, if you see, because of the N- layer which we have actually seen in the structure, if you see, we have seen that additional layer so-called N- region, which is nothing but drift region I said. So because of this particular drift layer, the current will be increased further in an aggressive way after IB5. See, in active region, it is slowly increased and later it has become constant. Whereas here in quasi-saturation region, the current will be increased in a linear way, in an aggressive way beyond IB5, and this is nothing but quasi-saturation region. So here, in between, this lies between hard saturation as well as active region, and this quasi-saturation region, the current is increasing in such a linear fashion. It is just because of that N- layer, so-called drift layer. And if you see the resistance of this particular quasi-saturation region, the transistor resistance will be very less. And if the resistance is less, in that case, the power losses are also less, which is an advantage. And later, if you see, the turn-off time of this particular BJT will be less in this quasi-saturation region. So, when the turn-off time is less, in that case, it can be operated at it can be used for high frequency applications. That means, when the turn-off time is less, the frequency it can be used for higher frequency applications. So, this is one of the advantage, and even this is an advantage. Resistance is less. When the resistance is less, in that what does that mean? The power losses will be less, since power losses is determined by the formula I square R. When the resistance is less, power losses are also less. So, in quasi-saturation region, it will not be going into complete saturation mode. So, that is the reason it is easy to bring the thyristor into the off state. So, by that, by that thing we can that is the only reason why we can use this particular transistor in quasi-saturation mode for high frequency applications as well as for low power rating applications. And then we have this hard saturation region. In this particular hard saturation region, this can be achieved by making emitter to base region forward bias as well as collector to base region also bringing it into the forward biased mode. We can achieve so-called hard saturation region. So this will be completely going into the saturation mode when the base current is beyond increased. In that case, the BJT will be going into the hard saturation region. So in this particular hard saturation region, the resistance offered is much lesser even when compared to that of the quasi-saturation region. So BJT operates in this particular region, the power losses will be minimum because the resistance is less. As the resistance is going on reducing, the power losses are less and it requires more time in order to turn off because it is going into the deep saturation mode. So the time required in order to turn off the thyristor will be more. So that is the reason this can be only used for the low frequency applications. So that is all about the different modes of operation of the transistor. And then in our next lecture, we will be seeing about MOSFET.